All right, in the last video, I talked about this delusion that we're trying to get rid of and the mathematics that gets rid of it. It might be a delusion to think that I can teach this kind of mathematics, but I think that I always feel like, well, if I know it, there's a lot of people out there a lot smarter than me. Why don't they know it? Well, when it was taught to me, I don't think they taught it right. They didn't. Uh, I think they went about it backwards. I mean, we were taught these ideas of symmetry, but they never actually gave a good description of what symmetry is. So, this guy named Bravais, he creates these 14 lattices. All right, well, what that represents is a set of different symmetries, and they can be represented by these objects. Well, what they really are is machines or symmetry operations. So you imagine that you can take an object and rotate it, or reflect it, or you break the object down into parts, and you can use those parts as a machine to do operations. So you have a set of symmetry operations. So in computer terms, it's you're creating sets, and then you're programming with those sets. That's your information. But that's not how they talk about it. But if you think about it that way, it's a lot easier because, this is a set of sets. It's a set of points. It's a set of lines. It's a set of planes. It's a set of faces. Okay? You can use any part of that. You can use any part of those sets, and you can create these operations. You create a code. That's what the Bravais lattice is. It's a set of codes, symmetry operations. They're formulas, they're functions, they're codes. Okay, so you can create this set of codes. Well, these 5 objects represent all possible perfect spatial symmetry in the universe. But if you look at it, you say, this isn't a set of 5 things, this is one set, okay? There's one set, and they all feed off each other. So it's a set of sets. We can imagine one symmetry operation that'll generate all 5 of these objects. So that's what we do. Boom, there it is. Now we've got an operator that we can use that can derive all these other operators. Well, that's not just a theory. I mean, you can reduce that to practice. You can mechanically demonstrate that. You can, theoretically, this is a set of sets. But you can take any 2 of these, and you can juxtapose them. So you can create a new higher set. So if you take the biggest one and the littlest one, you make a set with these 2. Okay? You can literally make a machine with it. Now the first, I could take 2 of these and make a set. Okay, and that's actually what you need to do with the double helix. If you understand the math of the double helix, you need 2 of these. Okay, so my first visualization of it was with this one inside of this, because this one's smaller than this. Okay, but this is kind of a bitch. See, it will work, but it's kind of a bitch. So why don't we do it this way instead and put the now mechanically works a lot better, okay? But still, you need to see the tetrahedron as a subset. Now, if you can do that, you can do this. Okay, well, which one do you like better? Well, I like this one better because I can see it better. I can understand it better. It's easier to break down. But this one's more powerful. This is the one that life uses because, see, crystals don't build outward with symmetry. They build by taking all possible symmetries and breaking them down. So a crystal wants to break it down. So if you take all possible symmetry, you first break it down to this. Now you can create a code like this. This mathematician Hamilton, he created a puzzle where the game was to traverse the go from point to point and then end up back where you started, a Hamiltonian circuit. Okay, well, you can do that kind of puzzle. You can do all kinds of puzzles. Games, you can play these games with these different sets of symmetrical features. Okay, so in that way, this is kind of like that. It's more like a puzzle. When I invented this, the very first thing I did was name it. I named it Code World. Okay, because it's a world that requires a code. Well, once you get to this stage here, now you've got a problem because there's an infinite number of ways to create this code. Okay? There's no single way to do it. The question is, what's the best way? Well, the best way is the way that allows you to speak the code. So what words do you have to say out loud to say this? And then if you want to move to another one, then you have to have words for that. It's like 2 + 2 = 4. We're going to do, it's a nonlinear number line. We're going to do math with it. We're going to go from one spot to another. So we have to name this spot, we have to name this spot. Well, the first question you need to have is how many spots are there? Well, if you have one dodecahedron, then you have 240 tetrahedrons. Okay? So we can figure that out by asking ourselves, how many pieces of the dodecahedron do we need, and how many pieces of the tetrahedron do we need before we can start creating individual names. Okay, then we need to say which of these sets are we going to use to make these names. Okay, so if we've got one dodecahedron and 240 tetrahedrons, see, we're going from 1 to 240. Well, if you look at the double helix and you say, what is its structure? Well, this is its structure. It's as if we drew a line from this point to this point. Now, all of a sudden, we've got this structure here. So we could see that it's a crystal that's basically stacking dodecahedrons. Well, if we see the protein as a crystal, it's stacking tetrahedrons. So now it's communicating the spatial information in the double helix to the spatial information in the protein. So it's converting dodecahedrons into tetrahedrons. Okay. So now we know that we're looking at a spatial code. It's the structure that's determining the sequences. Now we just need to know, how do you do that? Well, you can't do that by saying, when you say this sequence and this sequence, and you say CCC and proline, okay, you need to draw those sequences from the set of all possible sequences. Okay? You can't instantiate the code. That's like taking an Enigma machine, saying I already know the coded message and I know the uncoded message. Those are instantiations. So you can't say CCC is a codon, and you can't say that proline is its meaning. You can't say that this is a gene because you don't know what the gene might be. The gene might be anything. So you have to think of all possible molecules that could be in that instantiation. Well, if you start with this structure, then to instantiate this structure, you need 12 molecules. You need 12 different molecules for the nucleotides. Okay, you need a minimum of 20 amino acids if you want to put one in each of these locations. But the question is, what's the optimum number? Okay, if we were going to optimize this, what would be the optimum number? Well, the optimum number is 4. We need 4 nucleotides at a minimum. Okay, if we had 1 nucleotide, we would have this, and every codon would be the same. If we have 2 nucleotides, then we would have, I don't know, how many would we have? 8. We'd have 8 nucleotides. Okay, we have 3 nucleotides, and we would have 26 7 codons. Okay? If we have 4 nucleotides, we'll have 64 codons. See, we don't 64 is not this fixed number. That's the optimum number given the minimum required spatial information to make the double helix. Now, if you want to make the double helix, you need 2 of these because you need to have 2 tetrahedrons to get all 240 names. So you need to have a tetrahedron and its mirror. So you need to fill this structure with 12 different nucleotides. Then you need to get 12 more nucleotides that are the complements of those first 12. And then you need to make a mirrored structure. And then you've mathematically created the structure of the double helix, which is represented by this. 1 dodecahedron and 2 tetrahedrons. One of them's the mirror of the other. Well, the most efficient way to do that is this. So this is a mathematical model of the double helix. Okay, so if this is the codon table, then the codon table is overdetermined. In other words, we're not efficiently using the symbols that we have. If this is the codon table and it's the protein, then it's underdetermined. There are missing pieces. We know that because if we get a silent mutation, we get a different protein. So that means that this table is missing variables, it's missing pieces. So it's overdetermined on the double helix, and it's underdetermined on the protein. So now we know there's more information in the there's more information in the protein than there is in the double helix. But that just stands to reason. Life would want that. Life wants the most efficient, optimized, compressed spatial information for its information storage, which is the double helix. It needs all this spatial, it needs to uncompress it when it becomes life. Well, these proteins are these enormous amounts of spatial information. The sets are ginormous. Sets of proteins, the sets of things they can do, the sets of sets they can make. I mean, it just proliferates wildly. But that's how you go from 1 cell to 37 trillion cells. You have to fractally decompress the spatial information. This goes without saying. Okay, so as we step through the process of creating the code for Code World, we have to break spatial information. So we break it first from a dodecahedron to a cube. Then we have to break the dodecahedron. Then we have to break the cube. But each time we break it, we create information. It's the breaking that creates information. So the information in the genetic code is written in units of broken symmetry. Okay, they're not spatial coordinates. It's not like a crystal. In a crystal, it's breaking symmetry, but the atoms are literally spatial coordinates. In life, they're molecules. Okay, they're not single dots. They're clouds. Okay, crystals, regular crystals, do it retail. Life does it wholesale. You know, it's quantum entropy. It's quantizing. It's saying this is a quantum unit of spatial information. We can think of it as a quanta, A, C, G. Okay, we know it's not. It's this package. It's not a single point, but that's how atoms work. Okay, we can quantize them in crystals. It's one atom. Yeah, but it's a collection of spatial parts that are doing complex spatial computations. They're quantum computers. So these atoms are quantum computers that are calculating the answers to crystals. You take a set of atoms, you say, what crystal is this? Those quantum computers will go to work and say, here's the crystal. Okay, well, that's what they do in life, except they're way more complex. You have to think in more abstract mathematical terms. We're talking about symmetry breaking. That's what the code is. It's breaking symmetry down. It's taking sets of broken symmetry and it's using those sets as a code. So now we can start talking about using it. You know, if you really wanted to find the most efficient language for this machine, it's this right here, these playing cards. You can play this game, okay, more efficiently with these playing cards than you can with these colors, because these colors, you have to say red, red, red. With the playing cards, you just say ace of diamonds. Okay, if you say ace of diamonds, you've said red, red, red. You've said jack, queen, king. You said diamond, diamond, diamond. Okay, if you break it down into this language, this 4x5 placeholder system, you can play this game verbally, but you can also translate, because these code names translate into these molecule names. You can play this game right here using nothing but these molecule names. So you could say proline glycine there. This ball is now configured as proline glycine. You know, if I said lysine phenylalanine, there. Now it's lysine phenylalanine. That's the name of this configuration. But you can always make every position be 2 codons, but you can also make every path between 2 positions be 2 codons. So, you know, the solution to a puzzle might be proline glycine, which would be the same as green, yellow. But you'd go green, 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 yellow, yellow, yellow. That's the equivalent of green, yellow. Well, you can always break down the solutions to these puzzles. 2 codons plus 2 codons equals 2 codons. That's the addition and subtraction on a nonlinear number line. It's the math. It's the actual math, but you can play it with these playing cards more efficiently than those colors. But you can play it with these molecules. That's how I knew what it was. Oh my goodness. Look at you. So, yeah, I get it. I get it. It's very abstract. It's hard to understand. It's hard to follow. It's hard to believe, but it's mathematically true. You can verify it mathematically and mechanically. You can, you know, encode the code, and then you can use it as a machine language to run the code. Well, I don't know what else there is left to talk about. I mean, that's dead nuts proof right there. I get it. It's hard. It's hard to understand this stuff unless you're a freak, I guess. But at the same time, I mean, come on, a few professional mathematicians ought to be able to get together. Maybe they could refine this a little bit. I don't know. I'm not a professional mathematician, okay? But I can tell you right now, this code is the same as this code, is the same as this machine language, is the same as this map. When you start using this code to understand the map, okay, you can say all kinds of wild stuff on this map. I mean, like, for instance, you take this map and you say, well, there's codons and anticodons. Show me which is which. Well, they can't do that. Well, I can do that. I could say that every codon that is associated with this is associated with this. So this half of the map is codons and anticodons, and I can do the same with the other half of the map. So basically, I've converted a soccer ball into a baseball. It's binary. The codons pair with the anticodons symmetrically. You know, you could say that a DNA codon is 3 contiguous planes of a dodecahedron, and a tRNA codon is 4 contiguous planes of an icosahedron. And then you can give them names. This one's the 3 of hearts. This codon is the 3 of hearts. This amino acid is the 3 of hearts. And this tRNA codon is the 3 of hearts. And then you could say stuff about hearts. You could say stuff about clubs. You could say, how many codons does a club get? It gets 2. How do they feel about water? They all love water. Okay. How many codons does a 2 get? Well, it gets 6. Well, there's 6 of them that get 6, and they're all 2s except for the club, because the club's more important. The diamonds hate water. Okay. the weakest nucleotide in the set has start and stop. All the stops and the one start all include the jack of diamonds. Well, how do you know it's the weakest one? Because I encoded the code. I used a hierarchy of strengths to do it. I could say that the strongest part of the code is the most important part of the code. It uses all these tRNA codons to preserve it. It includes proline and glycine. Well, why? Because that's the lowest entropy grammar in a protein structure. So the grammar, the water loving, the water hating, the molecular weight, the size, the ability to make turns and sheets, that's all encoded mathematically in the code. Well, why is that true? Because the language has to be symmetrical, because it has to be able to make proteins out of other proteins. It has to be able to take one protein, cut it up and splice it together, and be sure that it's a good protein. It has to be able to read it forwards and backwards. You know, this is the most symmetrical language in the world, but that makes the search exponentially faster. It can search for proteins because of the pattern of these assignments. They're assigned specifically for that function. Okay, well, that's what I mean about a mathematical code. This code is mathematically correct. This is gibberish, just pure gibberish. Why? That's a dysfunctional delusion. This is a functional delusion. I'm seeing a code here. I'm seeing the most incredible code ever. This is the most interesting code. This is the most beautiful thing on earth. It's the most important thing in science. But the first thing you got to realize is math. It's a code. So, you know, they say, these guys say, where's your proof? I'm like, right there. Here it is, right here. Here's your code, buddy. Where's your code? And they go, well, it's right here. Every time we test it, it works. Every time you feed that sequence into your Enigma machine, you get a sequence out. That's great. I can do that too. This will do that, but it's different. And now we're actually looking at a code. So, like I say, now you can feel really comfortable about your new delusion, because now you know it's mathematically valid. So, you're welcome.